We're going to use mathematical induction to prove this. So we start with the basis step. Over here I should put for any integer n greater than or equal to 2. So the basis step here will be starting with the smallest, the least positive integer, which is 2. So we plug 2 into the left-hand side and the right-hand side. Make sure you realize that you understand that the left-hand side has more than just one term, possibly. So it depends on what n is. So if n is 2, we plug into this general formula. We get 2 minus 1 times 2. That is 1 times 2. So that tells us we only have the first term, because this formula is supposed to generate every single term in the sequence. So when we replace n with 2, we got the first number in the sequence, and so that tells us it's just going to be the first term. So that's left hand side equals 1 times 2, because we replace n with 1 and replace this n also with 1 right here, and it's 2. Now the right hand side, we replace n with 2. We get 2 times 2 minus 1 times 2 plus 1 divided by 3. So we get 2 times 1 times 3 divided by 3. So we cancel that, we get 2. So as we can see, this formula does hold for n equal to 2. So let me just write down here. So left hand side equals right hand side. Now let's do the inductive step. Again, because we are supposed to prove this for all integers n greater than or equal to 2, so which means we have to prove this formula holds for n equal to 2, n equal to 3, n equal to 4, n equal to 5, 6, 7, 8, 9, all the way to infinity. Again, we cannot do it like a basis step and prove it every single case, prove the formula is true for every single integer n. We have to use the inductive step. So in the inductive step, we assume this formula holds. So I'm going to go ahead and just write down the formula for n equal to k. So we assume the formula holds for n equal to k. Now we replace, we copy the first term, 1 times 2, the second term, 2 times 3, and dot, 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 plus the kth term. So when n is k, replace n with k. And the right-hand side, replace n with k, because there's only one term on the right-hand side. And our goal is to prove this formula holds for n equal to k plus 1. So let's replace n with k plus 1 and write down both sides. So the left-hand side, the first term is still 1 plus 2. Second term is 1 times 2. The second term is 2 times 3. Dot, dot, dot. And the last term, I'm going to save a little bit of space here because I want to write down the last 2 terms. Just like, we write down the first 2 terms, we also want to write down the last 2 terms here. So the last term, when n equals k plus 1, we replace this n and this n with k plus 1. So we get k plus 1 minus 1. That would just be k. And replace the next n with k plus 1. So we got k times k plus 1. Still the product of 2 consecutive integers. The previous term will be the n equal to k, because this one we got this because we replaced n with k plus 1. The previous term will be kth term, so we replace n with k. Now we get k minus 1 times k. And in this formula that we wrote down, we didn't really write down the last 2 terms. We only write down the last term because we don't really need to know what the second to the last term is. But the reason why do we need to write down the last 2 terms for the goal equation is because we have to compare the 2 left-hand sides. So this left-hand side, this whole thing, with this left-hand side, this whole thing, and to find out the relationship between them. And so as we can see, we have 1 times 1 times 2 plus 2 times 3, and then plus dot dot dot, and then plus k minus 1 times k minus 1 times k. So the first k terms of both left-hand sides, they match. The only thing they don't match is the last term. So now I understand, okay, if I want to prove the goal, I need to add this last term to the left side of what the given condition. This is like a given. Okay, so that's why we wrote down the last two terms. So let me get rid of all of these lines and write on the right hand side. So the right hand side we have to replace n with k plus well, let me get rid of that. Okay, so we're going to put this term right here, and we're going to put the right hand side and replace n with k plus 1. So we're going to replace this n, and that n with k plus 1. And so we get k plus 1 times k plus 1. Oh, sorry, it should be k plus 2 here. K plus 1 plus 1, that would be k plus 2. Okay, so now we can try to use the condition given. So this is like given, and this is what we need to prove. So like we observed before, this left-hand side in the given formula and the formula we're going to prove, they only have this term different. So I'm going to add this term to both sides. So let's add k times k plus 1 to the left-hand side. And we also add k to the k plus 1 to the right-hand side. After we add them, let's see what we can get. So the left-hand side is going to be 1 times 2 plus 2 times 3 plus dot 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 plus k minus 1 times k. So the whole left-hand side still needs to be copied because we are only adding a new term to the entire left-hand side. So we're going to add this term. And now if you take a look at the one we just obtained, that really matches the left-hand side in the goal equation. Now right-hand side, so this is what we are adding. Original left-hand side plus k times k plus 1. Okay, so we already got the left-hand side. What we need is to try to match the right-hand side. So, but when we look at them now, they look different. But we can use algebra to verify these two are the same. So we first of all try to do addition, equal denominator. So we're gonna find the LCD, which is 3 multiply 3 and 3, because the original denominator is 1. Any integer can be put as the integer itself over 1. So k is like k over 1. Okay, so we times both top and bottom by 3. Now we have a common denominator of 3. 1 times 3 is 3. So we will get, let's see here, common denominator 3. And the top, when we add the top, because I'm kind of out of space here, so I'm going to show you here. This is what we're going to add, numerators. By looking at the addition of these two, I realize they both have k plus 1 in common. Here is k plus 1. Here is k plus 1. They also have a k in common, k and k. So I'm going to factor out both k plus 1 and k. Factor out a k, factor out a k plus 1. So what we have left is just a k minus 1 plus 3. And if we work this out, k minus 1 plus 3, that's exactly k plus 2. And that is exactly what we have. So k times k plus 1 is the same as k plus 1 times k. So that tells us, okay, this whole left-hand side, if we copy it down, 1 times 2, 2 times 3, plus dot, 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 plus k minus 1 times k, plus k times k plus 1. This is equal to that, which is also equal to this. So that's how we proved it.